we're going to pick up where we left off now that we found it. This is our section on greatest common divisor and least common multiple. And we talked about one method of doing this last time, which is prime factorization method. You guys remember that one? That's probably the one that you're most familiar with. Maybe not, but probably. There are a few others we're going to take a look at today. The first one is division by primes method. And division by primes method will work no matter how many numbers we're trying to find the greatest common divisor or the least common multiple of. And what we do is this. We write the numbers in a row. So I'm going to write 410, 360. Your book sometimes puts a comma between them, do it or not. It's not the number 410,360. Maybe I'll erase it just for the sake of making that very clear. Oops, hang on. And then what we're going to do is we're going to divide down. Remember that division algorithm down that I did back in the last section? Where it's the sort of the alternate method of the factor tree? All right, so that's partly why we did that. So what we do is we look at the two numbers and we divide them by a prime factor. So what is a prime number that will divide both of these? 10. Okay, so 10 is not prime. 5 will work, or 2, either way. Eventually we're going to have both of them. So let's do 5 since I heard most people saying 5. What is 410 divided by 5? And 360 divided by 5? 72. 72? Yes. I'm taking y'all's word for it. I didn't divide by 5 first. Then we can divide by 2, right? Yes. All right, so what's 82 divided by 2? 41. And 72 divided by 2? 36. Now, 41 and 36. What happens? 41 is a prime number. That's a very good point. 41 is a prime number, which means unless 41 divides 36, which of course it can't because it's bigger, we're done. And the greatest common factor then, or greatest common divisor, is the 5 times 2. This method's really nice because you don't end up dividing back to just something that didn't matter. Obviously 36 divides back to 1%, right? But none of it's going to be in common with the other number, so we don't have to show it. How cool is that? Save time, it's good stuff. Alright, so this is division by primes method. Be careful. This one says prime factorization method. This one says division by primes method. Both of them divide by prime numbers, but they're different methods. Okay? Another class that I'm working with the same concept real recently, and they got too confused a lot because they sound very similar. Okay? Alright, the Euclidean algorithm is a really interesting one that you probably have not seen before. But it works really well, and it works really quickly, too, kind of like the last one. Here's what you do. You divide the larger number by the smaller one. Okay, so 72, we're trying to divide 126 by it. So how many times does 72 go into 126? Once, and I do multiply 1 times 72, 72, and I subtract. So what's 126 minus 72? 54. Now, one kind of just note right here is that the number here better be less than the number you're dividing by, or you've missed something. Probably the remainder issue for division, you remember? Then what you do is you take the remainder and the divisor, okay, that's the 72 on the outside, and you do the process again with the remainder on the outside and the divisor underneath. How many times will 54 go into 72? Once. Sometimes it goes in more than once. This is just an example. So what's 72 minus 54? 18. We take the divisor and the remainder. The quotient, the number on top, is not affected by any of this. I don't care that it went in once, but I do care what the remainder is. The remainder is dividing the quotient, I'm sorry, the divisor now. How many times will 18 go into 54? 3. And 3 times 18 is 54. So eventually, by doing this, I will get a remainder of 0. When I get a remainder of 0, the last number I divided by is the greatest common divisor.
Will you eventually get to 0, or?
Yes, we'll always get to 0. Whatever you divided by last will be the reason. Eventually, you will be zero. Obviously, the higher the factor they have in common, the quicker you'll get there, right? Okay, that's it for greatest common divisors. Next, we're looking at least common multiples. Now, let me pause here to remind you, I think I've said it before, but in case I haven't. Divisors are numbers that are smaller than the one you started with, right? They divide it. Multiples are numbers that are bigger than the one you started with. They're a multiple of it, a multiplication tables. So in other words, the multiples of 3 are 3, 6, 9, 12, 15, and so forth. They all start at 3, and every what we started with, and they get bigger from there. Divisors of, say, 20 are numbers that divide 20. They are 1, and 2, and 4, and 5, and 10. They're smaller than you started with. The words least and greatest are adjectives. You guys didn't know I knew that in my English. They're adjectives that describe the noun. Here's the credit. Adjectives that describe the noun divisor or describe the noun multiple. So a least common multiple is bigger than a greatest common divisor. Right? Don't think that the least and the greatest tell you how big things are. They don't. They're an adjective modifying the noun. Okay? So, least common multiples are big numbers, at least bigger than the numbers you're working with. And greatest common divisors are small numbers, smaller than the numbers you're working with. Everybody with me on that? Okay, I always have somebody that does them backwards. Not this semester. All right, so here's a couple of things. The least common multiple is the least non-zero whole number that's a multiple of the numbers in your set. The first method that I'm going to talk about, your book considers these two different methods, but they are really the same thing in terms of visual representation, so I'm including them underneath the same heading. One's called the number line method, and the other one's called the colored rods method. And what they do is they show multiples of numbers by the length, all right? So we're going to do 6 and 15 on the number line, and then I'll do 6 and 15 on the rods, so you can see that they really look a lot alike. I wanted to, let's see if I can remember where it is. Where is it? It's supposed to be underneath mathematics. There we go. So just put them all in the same spot, I'd be okay. And then I want mineral resources. I guess I know all this stuff isn't here because I don't ever use all these features. Where's the one I want, though? Oh, yeah. It's another button. Too many buttons. All right, this is the one that I want. Lovely that. I like this one because I can put my own increments on there. So I actually want them to be increments of 6. So I'm going to do 0, 6. So I'm doing multiples of 6, 12. What comes next? 18. 24. 36. Okay, I'm going to stop right there. I've got enough. And what we're going to do is we're going to take numbers, our number line. It's really a thick one. I don't know if that's thick. All right. We're going to do from 0 to 6. That's 1. Oh, you know what I should do? Oh, I know. Let's do this. There's 0 to 6. Make it a, I don't want, oh, actually, I should clone it. I actually wanted to make it a color. Right, I'm just messing around with it now. All right. Okay, forget it. Pretend it's colors. All right, so we're going to, I think I'd like Megan's suggestion, we're going to use the infinite cloner. And I need several of these guys. They should all be the same size if I use my infinite cloner, and I'm putting them step to step. So this is another piece that goes from 0 to 6, and then you've got one from 6 to 12. I've got one from 12 to 18, one from 18 to 24, 24 to 32, I'm sorry, 30, and then 30 to 36, 36 to, which would have been 42, and just for kicks, I've lost them in since I cloned them too many times. All right, so these are the different sort of leaps along the number line if you were taking leaps, right, that we're making. All right, the next one I'm going to do is I'm going to do the 15. So I actually don't have a 15 marked yet on my graph. But 15 would occur where? Yep, and halfway, right? So right here is 15. So I'm going to start here at the 0, and I'm going to go all the way to 15 and stop. And then we'll clone this one. We'll just clone it once. And supposing it worked, where'd it go? I don't know. Okay. All right, there's my other one. And then the next one would go from 15 to where? To 30. And you're actually done when they stop at the same spot. So the first place they stop is the least common multiple. Okay. So the least common multiple here of 6 and 15 is 30. Okay. Everybody with me on that? All we're doing is we're making jumps along the number lines at the size that it says. So I made jumps or leaps or arrows along the number line of size 6. I made jumps of size 15. And the first place where they stop in common will be the location of the least common multiple. There will be plenty of other places where they stop and things are in common, but I want the first one. Okay? Now, just the number line or the colored rods equivalent here, what your book does, and there are tools that do this, but what they do for a colored rods method is they actually draw a rod, sort of like a rectangle of size, what they call size 6. And then they would do that infinite cloning kind of capability. And they would make them go end to end. So we would line them up so that this is 6 and 6 together, which would be, I keep getting them together, it's going to move around for me today. Another one. So you guys can draw them better than I can on the screen, I think. All right, so they're stuck end to end. They all have the same size or length 6. And then I need another colored rod that would be the size or length of, not size, yeah, size or length is the right thing, of 15. Which would be roughly there. And then I take this piece and I make another one next to it. And I notice that all it takes is 2 of those, and they end at the 6th spot right here. This is 6, 6, 6, 6, and 6, which is 30. This is 15 and 15, which is 30, so the least common multiple is 30. Do you agree? It's the same method? One shows the rectangles and the other one shows the number line. They're the same thing though. All you're doing is trying to length of something. Once the lengths match, after adding it to itself a bunch of times, that's the least common multiple. And this is great when the numbers are small. I'm happy enough to do this. But if the numbers are larger, I don't want to. I don't know about you. I don't want to draw something that's 15 long compared to something that's 35 long. You're drawing all day. It's a mess. So we need some other sort of algebraic ways of thinking or numerical ways of thinking aside from drawing a picture for it. And so there's other methods. The next one, again, has some sort of the feature that it's very easy to see what's happening, but not so much working with this in an infinite way is that we write out the multiples. This is like writing your multiplication tables back in 3rd grade. Okay, so I know you probably didn't do 12 and 15, although 12 is a multiplication table that is done these days. But you're imagining adding this number to itself repeatedly, or multiplying it by all the increasing digits, natural numbers. So after 12, you would get 24, and then 36, and then let's get a couple more. After 60, and these would keep going. And this is like a sequence, right? We've done sequences before in class. We're making a sequence. How about 15? When we start at 15, what's the next one? And then the next one would be 75, and when I do one more would be 90, right? Now, you can actually stop when they match. So where do they first match? 60. So the least common multiple is 60. And this works again really well as long as they match up fairly quickly. But you don't want to be writing these lists if they don't match up fairly quickly. So what happens then if we have numbers that don't match up as quickly? Not necessarily that these don't, but I need to show you other methods that would be helpful if they didn't match up so quickly. Prime factorization, we've seen that one before, right? We saw that for greatest common divisors. We're going to find the prime factors of each of these. So let's start with 90. Smallest number that divides 90. Prime number. Smaller. Smaller. There you go. Okay, 90 divided by 2. 45. And then smallest number that divides 45. 5 does, but I'm going to go 3 because 3 is smaller. 45 divided by 3? 15. That's 15. Smallest that divides 15? 3. And then I get the 5 that you guys have been egging to get all the way along. So, in fact, I'll write these out in a minute, but let me just do all the factor downs for each one, okay? The next one's 50. Smallest number that divides 50? 2. And I get? 25. All right, and then after 25 I get? 5. And? 5. Good. Now let's do 20. Smallest that divides 20? And I get? 10. And then 10 I get? 2. And I get? 5. All right, so these are the prime factorizations for them. Everybody's good on that? Awesome. So we're going to write each of them out. So 90 was 2 times 3 squared times 5. 50 was 2 times 5 squared. And 20 was 2 squared times 5. They have some things in common. They have some things not in common. When we were doing greatest common divisor, what we did is we said, what do they have in common? And we worked only with that. Remember that? All right, least common multiple, that is not what we do. For the least common multiple, we actually look at everything they have, period. So what are all of the bases that they have? Not just in common, but everything. 2. I got a 2 and a 3 is next, and then a 5. They have a 2, a 3, and a 5. It's not a matter of what they have in common. It's a matter of anything that's present at all. So you write every base that they have down. This is different, right? 3 is common divisors. You only write down what they have in common. Least common multiples, you have to write down everything that any of them have. Then you have to write exponents on them. Greatest common divisor, what exponent did we choose? The least. We chose the smallest exponent. With the least common multiple, we picked the greatest. What is the greatest exponent on 2? 2. Greatest exponent on 3? 2. And greatest exponent on 5? 2. And of course, they're not always 2's. So grab a calculator, tell me, what is 2 squared times 3 squared times 5 squared? It is. So the least common multiple of 90, 50, and 20 is 900. I wouldn't mind writing multiples of 90 out, so I got to 900. I mean, it would take me a little while, but I do not want to write multiples of 100. I write multiples to 900 for the number 20. It's going to take forever. So the method you saw previously would not be quite so helpful with these particular numbers, right? Yes. Good. Okay, let me do division by primes. Okay, so we've seen division by primes, right? We did it the very first thing we did today, actually, on this particular lesson today, is we looked at writing the numbers beside each other. Now, I actually have 3 numbers, which is fine. I can write 3 numbers beside each other, so I'm going to do that. I write my 3 numbers beside each other. And I look for what do they have in common. So what factor do they have in common? 5. Okay, so we'll do 5. All right, so what's 90 divided by 5? It is 18. How about 100 divided by 5? 20. And 20 divided by 5? 4. Now, 18, 20, and 4. What do 18? They have a 2 in common. Okay, what's 18 divided by 2? 20 divided by 2?
10.
4 divided by 2? 2. Now, 9, 2, and 12, 9, 10, and 2 don't have anything in common. But 2 of them do, right? So look back up here on step 3. It says divide all quotients by a common prime factor. Any factor that divides at least 2 of the numbers can be used to divide. So we're going to do this again. 10 and 2 are both divisible by 2. So you might look at this and say, but 9 isn't, and you're correct. So we're just going to rewrite the 9. We don't do anything with him. If he doesn't divide, he just gets rewritten. We don't have to deal with him. But 10 does divide by 2, so I get 5. And 2 divides by 2 to give me 1. And at this point now, 9, 5, and 1 don't have anything in common to any of them. Okay, so here's the cool thing. I like this method because the least common multiple is all those numbers multiplied. So when I did the greatest common divisor, it was just the numbers on the left, and I didn't do anything on the bottom, right? So with least common multiple, with least common multiple, I get all the divisors that I used on the side, and I get all the quotients that are on the bottom. So I end up with 5 times 2 times 2 times 9 times 5 times technically 1. And this one happens to be here as well, yeah.
Wait, did you just say why we don't do an exponent?
I don't need any exponents. I'm just writing them all down by themselves. I mean, I could write 2 squared, but it doesn't help me for the most time out anyway. Okay. There's a formula that relates greatest common divisors and least common multiples. And there's a couple ways to see it, but let me show you the one your book is using. The greatest common divisor of 2 numbers times the least common multiple of 2 numbers equals the 2 numbers multiplied together. Which is really handy because that means if you find one of them, you can find the other one without going through the rest of the process. I don't know about you, that's very intriguing because I would like to do this as little as possible if I can, and this one allows you to do that. 72 and 126 we did before. Go back up to example 4 and tell me what is the greatest common divisor of 72 and 126? 18. 18. So in other words, if I want to find the least common multiple, I can take 18, because it's the greatest common divisor, times the least common multiple. And if you want to write least common multiple 72 is 126, that's fine. And this should equal 72 times 126. How do I solve for the least common multiple? I'll divide by 18. So what I need is I need to multiply 72 times 126 and divide by 18. I don't have to do prime factors. I don't have to divide anything over again. I just do 72 times 126 over 18. And it will be a whole number. If it isn't, you've got an error somewhere, probably back in your divisor work. So that's what a question is.
Try to find the least common multiple. So do we go ahead and do that?
Yes, please. Did you get one?
504.
5:04?
Yeah.
I heard an echo as though two of you found this. That's good. 5:04. Okay. I think I have time for one more. Two bike riders. The application problem. You guys love these, so I should do one. Two bike riders ride around a circular path. The first rider completes one round in 12 minutes. The second completes it in 18. Evidently much slower, right? If they both start at the same place at the same time, and they go the same direction, after how many minutes will they meet again at the starting place? So this is actually asking for the least common multiple. It's the first time that they have a multiple in common. So one person goes around 3 times, the other goes around 4 times. Maybe that's what's going on. But this is asking you for the least common multiple. So I'm going to do a division of primes because I think it works nicely. But you can do it with whatever method because it doesn't tell you. 12 and 18 are both divisible by? 3. Okay, we'll go 3. 12 divided by 3 is? 18 divided by 3? 4 and 6 are both divisible by? 4 divided by 2? 6 divided by 2? And 2 and 3 do not have anything in common, right? So how do I find my least common multiple from this? So it's all of these guys. And what is 3 times 2 times 2 times 3? 36. That's the number of minutes it takes. And in fact, that would exactly put first guy going around 3 times, right? We'll go 3 times in 36 minutes. And person number 2 going around twice. So they will meet again in 36 minutes.